This video explains how a side-looking airborne radar works. Airborne radars are categorized into side-looking airborne radars, SLAR, and forward-looking airborne radar, FLAR. Both systems can be operated with a real aperture as well as with a synthetic aperture. The only difference is in the software and in the application. The content of this video is the side-looking airborne radar, SLAR. A side-looking radar is a high-resolution imaging radar that uses a real aperture. This active sensor has antennas positioned in a plane that is perpendicular to the aircraft's axis and flight path. Like any radar system, it can transmit and receive signals regardless of daylight and weather conditions, allowing it to generate high-resolution strip maps of the ground. It is particularly effective for mapping larger areas of terrain with photo-like detail. Originally, the side-looking radar had military significance because it could conduct surveillance well beyond borders and front lines without placing the aircraft in the danger zone of enemy fire. The expertise gained from using side-looking radar is now applied in civilian remote sensing of the Earth. Compared to a rotating surveillance radar that scans with the polar coordinates azimuth angle and range, the side-looking airborne radar has a Cartesian representation with the values in the flight direction along track, as x-axis, and at right angles to it across track, as y-axis. The functionality of the two radar systems is identical, and the radar signal processing is also largely the same. The antenna of the side-looking radar transmits a short signal that has a fan-shaped power distribution. Only a small portion of the antenna's pattern contains the transmission energy, which is referred to as the pulse volume. When this transmission pulse encounters a reflective object, some of the signal is scattered back toward the aircraft. The intensity of the signal primarily depends on the distance between the antenna and the reflecting object. Given that the flight altitude, typically in the hundreds of meters, is much smaller than the desired ground range of 10 to 100 kilometers, the side lobe directly beneath the aircraft generates a type of initial impulse. This pulse represents the time it takes for the signal to travel to the flight altitude. Following this initial impulse, there is a brief silence until the first echo from the main lobe is received. The angles alpha 1 for the near range and alpha 2 for the far range are not determined through direct angle measurement, rather, they are calculated solely based on the runtime measurement, which effectively serves as a distance measurement. The amplitudes of echo signals received in succession follow the laws of the radar equation, which state that they decrease in inverse proportion to the fourth power of the distance. However, as the distance increases, the pulse volume also increases, leading to a larger radar cross-section at long ranges. Unlike weather radar, which detects real volume targets, the targets here are not real volumes. Consequently, the amplitude, depending on the characteristics of the reflecting objects, particularly their roughness and the orientation of their reflective surfaces, decreases more approximately in inverse proportion to the third power of the distance. As with any radar, the slant range r is not equal to the ground range. The ground range of the reflecting object is often denoted by the Greek letter rho. The received time-resolved radar signal contains information on the impulse response perpendicular to the direction of flight and, after processing, generates a line of the radar image. The processing of the next line in the radar image does not begin until the aircraft has flown a certain distance further. By repeating this process, a two-dimensional image of the radar pulses scattered on the ground is created. The area swept by the radar is called the ground swath. The footprint is the area illuminated by the radar in the respective pulse period. The footprint is not the same as the swath width or the strip width of the imaging strip. The horizontal distance that can be used for image generation in practice includes only the widths where the various footprints leave no gap. The swath width is obtained from the horizontal antenna pattern and the flight speed. The horizontal antenna pattern can be derived from the antenna length L. Caution: when observing, the beam angle or nadir angle theta is not always equal to the angle of incidence or incidence angle theta I. Not only because the Earth is not flat and the two perpendicular lines are not parallel, but mainly because the beam angle often only describes the center of the antenna pattern. Often a distinction is then made between a local angle of incidence and a general angle of incidence, which is complementary to the beam angle. A local angle of incidence also depends on the beam angle, but changes depending on whether the reflecting object is in the near or far swath. The echo signals are stronger at closer ranges compared to farther ranges. However, at very large distances, the signals become significantly weaker, and the geometrically resolved ground elements, or pixels, increase in size. This leads to an upper limit on the possible scanning range. In the accompanying graphic, the pixels are intentionally depicted as larger than usual for clarity. In reality, their size is typically in the order of a few meters, with a swath width spanning several 10 kilometers. A line can contain several thousand pixels. The picture shows the E-8 aircraft from Northrop Grumman with the J-STARS side-looking airborne radar. The radar is capable of displaying two objects as separate entities only if they are not both located within the main lobe simultaneously. The approximate horizontal antenna half-power beamwidth theta A is proportional to the ratio of the length of the antenna to the wavelength. For different types of antenna, this ratio can be easily multiplied by an empirically determined factor. For practical reasons, the antenna length cannot be increased indefinitely, so a side-looking radar with a real aperture is only suitable for low altitudes where the distance between the antenna and the terrain is not too large. A factor of 70 can be used to estimate the half-power beamwidth of the main lobe of a phased array antenna at the center of the beam. For the J-STAR antenna, which has a length of 7.3 meters and operates at a wavelength of 3 centimeters, the approximate minimum half-power beamwidth in the horizontal bearing angle is 0.3 degrees. In the vertical direction, there is only 2 feet, approximately 0.6 meters, of available space. Using the same formula, the vertical beamwidth of the antenna pattern is about 3.5 degrees. As a result, the radar transmits in a typical fan beam configuration, featuring a very narrow horizontal beam and a slightly wider vertical beam. The resolution in flight direction is called along-track resolution or sometimes cross-range resolution because it is perpendicular to the scanline. It depends on the slant range and the beamwidth of the antenna. The points of the antenna's half-power beamwidth to the origin form an isosceles triangle that can be divided into two equal right triangles. For one of these triangles, we apply the sine function for half the beamwidth. This equation can be simplified by an approximation because the sine of a very small angle can be set equal to the angle value itself with sufficient accuracy. After that, the two 2's cancel each other out. However, the value of the angle must now be entered as a radian. 0.3 degrees corresponds approximately to 0.005 radian. At the ground, these 0.3 degrees at a distance of 10 kilometers result in a minimally resolvable range difference of 50 meters. The same radar in a satellite would result in a resolution of 5 kilometers at a distance of 1,000 kilometers, which is out of the question for practical use. The slant range can be resolved trigonometrically into the quotient of the flight altitude and the cosine of the angle of incidence. It is therefore also of a different size in different areas of an SLAR image. The across-track resolution is comparable to the range resolution of a ground-based radar. It is a function of the speed of light and the pulse length, or, in the case of intrapulse modulated radar, the compressed pulse length. The factor 2 in the denominator is explained by the wave's outward and return path. The horizontal resolution on the ground also depends on the local angle of incidence theta, I, and can be calculated using an angle function. At close range, the resolution should be somewhat poorer than at long range. This also explains why possible radiation directly downwards would have an angle of incidence of 0, so this direction could not be evaluated due to the division by 0. The two dimensions of resolution produce areas on the ground that are limited by the minimum pixel size in the flight direction, angular resolution, and perpendicular to the flight direction, in terms of distance. To ensure that these pixels are approximately square, The flight speed, pulse duration, and pulse repetition frequency must be matched to one another. Matching the pulse repetition frequency limits the maximum unambiguous range and the maximum width of the imaging strip. The range resolution deteriorates at the near swath, the angular resolution at the far swath. The mean distance of the image strip should be selected from these two values to ensure that the single pixels are approximately square. In this example, that would be approximately 5.5 kilometers. The range resolution deteriorates at the near swath, the angular resolution at the far swath. The mean distance of the image strip should be selected from these two values to ensure that the single pixels are approximately square. In this example, that would be approximately 5.5 kilometers. To evaluate the echo strength, a normalized radar cross-section sigma-0 is introduced, which defines the radar cross-section sigma per unit area. The values delta x and delta y denote the pixel dimensions. This normalized radar cross-section sigma-0 depends, like the radar cross-section in air surveillance radars, on the frequency and polarization of the incident wave, on the angle of incidence, and on the electrical and geometric data of the observed surface, etc. The surface roughness is a key factor in reflected signal strength. With a smooth surface, the electromagnetic wave is reflected according to the basic rule of reflection. The angle of incidence is equal to the angle of reflection. The radar receives nothing from such a surface. But no surface is really completely smooth. These irregularities can only be ignored if they are very small to the wavelength. At a wavelength of 3 centimeters, these irregularities would have to be smaller than 1 millimeter to be ignorable. This means that this surface property is always frequency dependent. A surface with irregularities of size of a ½ inch can be considered rough in the X band, but possibly not in the C or L band. With an intermediate rough surface, a larger portion of the incoming wave is reflected in directions that the radar cannot utilize, but a smaller, yet analyzable, portion is received. When a surface is very rough, incident energy scatters in all directions in a statistical and equal manner. As a result, the radar can detect a comparatively larger portion of this energy as an echo signal. This effect is used in the detection of oil pollution at sea. Oil changes the roughness of the water surface, and the radar detects the poorer reflection from the dark color of the surface. Often, the polluter can be identified immediately because they produce a very strong, bright signal in the image. Evaluating echo signals in a maritime environment is easy. However, on land, presenting single measured values in a clear and interpretable manner can be challenging due to the often significant variations in heights. When measuring in a slant range, side-looking radar receives echoes from higher terrain elevations before it receives echoes from objects located at lower elevations. As a result, the distances measured in the radar image are not represented in actual proportions, leading to distortion caused by so-called foreshortening. For instance, consider a mountain slope that tilts towards the radar. The length of this slope, measured from the summit point, B, to the foot point, A, appears compressed in the image, covering the distance from displayed point A to displayed point B. Conversely, the slope that faces away from the radar, extending from displayed point B to displayed point C, appears stretched. A layover occurs when the terrain is so steep that the distance, slant range, to the mountain top, point B, is shorter than the distance to the foot of the mountain, point A. In the radar image, the order of these 2 points is even reversed, showing point B in front of point A in the distance. The steeper the beam angle, the more likely this effect will happen. Therefore, when selecting the beam angle, it is important to balance the reduced resolution caused by larger distances and the overlaps resulting from shorter distances. Larger distances have another disadvantage: the angled illumination of terrain elevations creates a shadow effect. Nothing can reflect in this shadow, causing the area to appear dark in the radar image. The flatter the incoming radiation, the larger the angle of incidence becomes. As the angle of incidence increases, the shadows of the objects become longer. The side-looking airborne radar is an early method for remote sensing of the Earth. Like all radar, it has the advantage over visual reconnaissance of being able to conduct surveillance in the dark and through fog or smoke. The angular resolution is rather poor, which is why only low flight altitudes and detection ranges are useful. Perspective distortions such as foreshortening, layover, and shadows make it difficult to evaluate the radar image. Therefore, a side-looking radar with a real aperture is not suitable for use in satellites. Side-looking radars can be upgraded to synthetic aperture radars, SAR, by utilizing appropriate software. Although these radars have a wide antenna pattern, the SAR technique significantly improves angular resolution, enabling the use of satellite platforms for remote sensing applications. More details on this topic will be covered in one of the upcoming videos. I hope you enjoyed this video. Thank you for watching.